Hi everyone! In this video we're going to talk about something called integration through substitution. This is going to let us integrate more complex expressions than we've been used to. Take a moment and find the derivative of this function, 6x squared plus 1 to the fourth. So hopefully you were able to use the chain rule. Our outer function is something to the fourth, so the derivative of something to the fourth is 4 times that something to the third, but then of course we have to multiply by the derivative of the inner function, which is 12x. So let's take a look at this integral. You're probably able to recognize, oh, well, I just took the derivative of 6x squared plus 1 to the fourth, and I ended up with this expression, so the antiderivative of 4 times 6x squared plus 1 to the third times 12x has got to be 6x squared plus 1 to the fourth. And then, of course, we have our plus c. But if we hadn't just taken this derivative, it probably would be a little bit difficult to recognize what's going on here. So take a minute to think about, why is this different than some of the integrals we've been working with? The previous example is integrating a composite function, which we haven't done yet. We've been doing things like x to the n, but we haven't really been doing things where we're integrating a function raised to a power or something kind of similar to that. So we're going to learn a method of integration called u-substitution, which is going to help us integrate composite functions. The way to integrate composite functions is just to kind of go through the opposite of the chain rule. So there's actually no product or quotient rule for integration. So our best bet for more complex functions is through u-substitution. So this is the reverse of the chain rule. If I have a composite function multiplied by the derivative of the inner function, the answer to that is the antiderivative of the composite function. So here f is the antiderivative of little f. The way we're going to be doing this is through actually rewriting the expression in terms of other variables. U is usually what's used through it. You could use any variable you wanted that to, but u is kind of like the standard variable across calculus. So we're going to rewrite the integral in terms of u and du to turn it into a simpler thing to work with. So let's look at the example from the warm-up again, and we're going to do this problem using u-substitution. It's going to turn it into a simpler integral to work with. First thing I need to do is kind of redefine a function in this integral to be u. So if I let u equal 6x squared, the derivative of that is 12x. This is kind of is a little, the trickiest part here is like this du dx, or the derivative of u with respect to x, is 12x. So du equals 12x dx. That kind of comes from just multiplying both sides by dx. And what that lets us do is take this whole expression, this 12x dx, and turn it into du. So, and wherever I see this this 12x dx, that's gonna get replaced by du. And this 6x squared plus 1, I'm gonna rewrite that as u. So if I do that, I have a nice integral of 4u to the third du. We know how to integrate 4u cubed du. That's just u to the fourth plus your constant of integration. And so the last step here is just to substitute our expression for u back in. So instead of writing u to the fourth, I'm going to rewrite it as 6x squared plus 1 to the fourth plus c. So the whole point of this is just to turn it into something that's a little simpler to integrate. The key here is just identifying u. It's to find a function in the integrand whose derivative is also there. The way to do this is usually to identify the inner function. of a composite function within the integral, and the derivative of that usually kind of falls into place. So we're going to walk through two more examples together. Let's take a look at this one. First thing I want to do is identify u. I want to identify an inner function whose derivative is also there. Oops, sorry. So if I look at this 10x right here, that's the derivative of 5x squared plus 1. So if I let u equal 5x squared plus 1, the derivative of that is going to be 10x. So what I can now do is, instead of this 10x dx, I can write that as du. And instead of this 5x squared plus 1, I can write that as u. So this turns into the integral of u cubed du. And I didn't touch on this before, but I guess I should now. The whole point of rewriting this du is because this, whatever this is, this d whatever, it has to be the same as your variable in the function you're integrating. So I can't have a u cubed dx and get the same answer. So that's the whole point of turning it into u and du instead of just u and dx, because we need these to be the same. So anyway, integral of u cubed du is 1/4 u to the 4th plus c. But our final step is, instead of leaving our answer in terms of u, we want to rewrite it by substituting our u expression back in. So this is our final answer. And a good way to check your work, if you take the derivative of this, you should get what was in the original integrand. If you don't, then that tells you you did something wrong. Let's do one more example together. Whenever we've got a square root, it's always a good idea to rewrite it as a power, because that's going to make it easier for us to integrate. So take a moment to see if you can identify u and du. So hopefully you're identifying here that our inner function, the function that's actually being raised to the power, is 6x plus 1. And the derivative of 6x plus 1 is this 6. So what that means, instead of writing 6 dx, I can write that as du. And instead of this 6x plus 1, I can rewrite that as u. So this turns into the integral of u to the 1/2 du. Again, that 6 dx is written as du, and that 6x plus 1 is written as u. So then we know how to integrate u to the 1/2. It's the same as the integral of x to the 1/2. It's going to be 2/3 u to the 3/2 plus c. And then our final step, instead of leaving our answer in terms of u, we want to write it as an expression involving x. So our final answer is 2/3 times 6x plus 1 to the 3/2. So hopefully this gives you an idea of what's involved with integration through substitution.